Good afternoon to all IEM and UEM family members once again. So today alongside me is Professor Sasthi Hens. Sasthi is going to present a topic, case study on blowholes, blowhole rather. So this is not the blowhole that we know about wells or the other animals of that category who breathe using those blowholes. It is the holes that is on the casting surfaces, as I could understand from him, the holes on casting surfaces that he is going to talk about. So Professor Sasthi, I believe that you will make it easy for all other professors or teachers who are belonging from other departments. They will also take full interest in your topic. Thank you for coming up today. So you take over from here.
Okay, thank you, sir. Good afternoon, everyone. First of all, I want to thank every faculty members for giving me this platform to share my knowledge. My topic for discussion is case study on blowhole. When we want to manufacture any product, there are lots of processes available for us. Including them, there are some processes available which convert raw materials or scrap material to a basic primary shaped and sized product. And these processes are called the primary manufacturing process, like casting, welding, forming, etc. Now, for further improvement on the product, we use another processes like for further improvement of properties, surface quality, dimensional accuracy, tolerance, etc. We use advanced processes, and these are called secondary manufacturing process. Like the machining or the surface improvement process like heat treatment, coating, etc. Now my topic here is blowhole, which is a kind of defect occur in cast product. So before going to discuss in detail of this case study, first I want to briefly discuss about casting process. Now, metal casting is the oldest manufacturing process. It was in practice around 5000 BC in the ancient Mesopotamia or ancient Egypt culture. And now today its application include all areas of human requirements. We have applications of metal casting in the automotive industry. The automotive engine are manufactured by metal casting. The aircraft engine are manufactured by metal casting. The turbine housing, machine tool structure, and many more are manufactured by metal casting. So first I want to discuss something about briefly. I want to discuss briefly about the metal casting process, basic concept of this. So here in this flow diagram, the processes are mentioned. Like the first, it's required to prepare the mold. Okay, generally we follow some specified steps to make any product by casting process. Okay, so the first one, this is making the mold. Okay, so for making the mold, it is required to prepare first the pattern. And pattern, this is some wooden or metallic piece, which is nothing but the replica of the job, but the dimension of the pattern is something different compared to the product. And this difference, this is called the allowance. Okay, we prepare the pattern by wood, metal, or sometimes we also use other materials like plaster of Paris, plus plastics, etc. Okay, so this is the replica of the job with some allowances. So the first thing, it is required to prepare the pattern. And now if it is there are some holes are available in the product, then we prepare the core. Okay, core, this is also prepared by the molding sand. So with pattern, generally we prepare the mold. Okay, and that means the cavity in between the mold. Okay, and after that we place the core in between that. And not only the cavity or core, they are also required some channel through which we pass the liquid material. Okay, this channel, this is properly designed, and this is called the gating system. Okay, so with gating system, the cavity, this is one stage. Okay, after that we melt the material through which we prepare the product. Okay, after melting, we pour the liquid material through this channel in between the cavity, which we prepare by the pattern. So after pouring, obviously after some time their solidification happen, and after solidification, by breaking the mold, we remove the product. Okay, not only the product, with product we also get the material, the solidified material available in the getting system. Okay, so there are also some further steps are required to follow, like in the fettling shop we trim the unwanted parts from the product, and after that if it's required machining, then we do that, and finally this is cleaning and inspection. So these are the steps generally required to follow for casting process. Okay, this is the process for sand mold casting. Now in this diagram, this flow diagram, the all the processes also mentioned here. Like this is the finished product, it is required to prepare by the casting process. So for making this product, what's the steps we follow? First we will make the pattern. Okay, now there, this is the core box. For if some hollow portion is available in the product, so we make it by using the core, and we prepare the core by using the molding sand, and we make it in the core box. Okay, so this is the sand. This is the molding sand. For preparation of the molding sand, generally different ingredients we use, like the silica sand, clay, moisture, some inorganic and organic binders. Okay, so these are the ingredients by which we prepare the sand, molding sand. So these are the flask, there we prepare the mold. Okay, so by the pattern here we prepare the cavity, then in between the cavity we place the core, then also we prepare the gating system. This is the pouring basin, then sprue, this is runner, gate, and the cavity. Okay, so this is the complete channel through which we the liquid material can flow, and it will fill the cavity. Okay, after preparation of this gating system, then we pour the liquid material in it, and after solidification we will get the product. Okay, so this is the complete process, that means the specified rules required to follow for making the cast product. Here also in this figure the same thing. Here there are two flasks, one this is cope and drag, there are two flasks, and this is the cavity. Okay, and this is the cavity for the product. Here this is the core for making the hollow product. Here this is the pouring basin, then the sprue, then runner, here it is the riser. Okay, then cavity, and here also there another riser. Okay, so through this channel by the ladle we pour the liquid material, and after solidification we get the product. Okay, so when we study about the casting process, obviously we will use it when we'll get that means different advantages compared to other manufacturing processes. So the study of the advantages and also the disadvantages is very much required. So when we say about the advantages of metal casting, the first one, this is intricate shapes can be made. What about the intricate shape? Like there are so many products are available where which one is not possible to prepare by using the other manufacturing processes. Like suppose some product, that means the dimensions or the shapes is shape, this is very complicated, so it's not possible to make by using the machining process. Okay, but that kind of products we can make easily by using the casting process. Okay, so it's possible. This is very good advantage of casting compared to other processes. Now the next one, flexibility of size and weight. This is another one very important, flexibility of size and weight. Okay, when you say about the flexibility, that means different size and weight of product we can make. Like if you say about the jewelry product casting, okay, the weight of the product is few gram. Okay, and if you say about the turbine blade or the turbine housing, there the weight, this is few ton. Okay, so both this product is possible to prepare by the casting process, so which is not it's not possible to make this kind of products, that kind of versatility by other processes. This is possible only by the casting process. Now the next one, this is simple and inexpensive tools. Here for that means continuation of all the steps, like preparation of pattern, preparation of mold, melting the material, pouring the material, and after solidification some other operations like fettling operation we do in the fettling shop, inspection. So in each and every stages, the tools we use, the process, all these things are very simple. Okay, so this simple and inexpensive tools we use for this process. This is another advantage compared to the other processes. Now here the production rate is very high. Any material can be cast, so all types of material we can use for casting, like ferrous and non-ferrous metals, and wastage of raw materials is less. Okay, so here, like if you say about the machining process, what we do generally, we remove the unwanted parts, unwanted material from the stock or the raw materials. Okay, so this removed material, this is kind of waste. Okay, this is scrap. Okay, this is, you can say that, the loss. But in case of the casting, what happened, we took only that much of material which is required for the product and the getting system only. And also after preparation of the product, we trim the unwanted parts, this getting system, from the product, and we can reuse it. So this is another great advantage. There the wastage of raw materials is less. So these are the important and advantages we get by using the casting process. Now here the demerits of metal casting, this is also very much important, because uh, after study of the demerits, there the further modifications happen and new technology comes in market. So demerits are very much important. So the first one, the demerits related to casting process, the labor intensive process. So each and every stage, preparation of pattern, preparation of mold, then melting, solidification, each and every stages, they are required huge number of labors. Okay, so this is one kind, that means this is the disadvantage with related to this process. Now the dimensional accuracy not so good. Here actually the surface dimensional accuracy and the surface finish are not so much good, because the surface, this is just the impression of the surface of sand. Okay, so the sand surface, this is not smooth, this is uneven. So related to that, the surface of the product is also rough. Okay, so this is one disadvantage. And to that means eliminate this kind of problem, what we make the product with something larger dimension, so that much of large dimension we can machine, okay, and get the final required dimension. So this is the that means solution for eliminate this kind of problem. Okay, now requires close process control. Now here this is very important, requires very close process control for each and every stages. It's required to properly maintain all the that means process. Okay, like if you say about the preparation of the molding sand, okay, there are different ingredients we use. Now if the proportion of the ingredients it's not proper, then ultimately it the product. Like suppose they are the ingredients we use: sand, then clay, moisture, and the binders. Okay, now if the clay percentage is very high, what happen? Obviously when the clay percentage is high in the molding sand, then we'll get higher strength on the sand. But at the same time, what happen, we'll compromise with the porosity in between the sand grains. So when we'll compromise with the porosity, what happen? Actually when molten metal comes in contact with the molding sand, there are different ingredients we use which will burn, like the oil or the coal dust or wood flour. So due to burning, there are huge amount of gases develop, and also the moisture available there, this will convert into the vapor. So if this moisture or the gases cannot escape from this cavity place, so what happens? So this will entrap in between the product, so ultimately it will make some defective product. Okay, so that's why it's required to, that means, mix the ingredients with proper ratio. If the moisture that means water percentage is high, then huge amount of vapor develop, and also some amount of this vapor can escape and some it will entrap in between the cavity. So also this will make the defective product. Okay, so like that, for each and every stages it is required to properly control the processes. Okay, so this is another disadvantage, you can say. And the last one, this is defects like blowholes, hot tearing, misrun, inclusions, metallic projections, shrinkage, porosity, etc. So except that, many other defects can also happen. So these are the defects, the important defects generally develop on the cast product if we not properly maintain the process. Okay, so these are very important defects. Now here in the next slide, The first image, this is blowhole. What happened here? On the surface of the product, you can see there are some holes or pores are available. Okay, this is called the blowhole. So why this kind of problem occur? I already told, when the entrapped gas cannot escape from the cavity. Okay, so then it get, that means give impression on the product surface. Okay, so this is the problem, blowhole. So to eliminate this problem, we have to properly, that means we have to properly maintain the porosity, and to increase the porosity, generally we can externally make some holes, okay, to increase the porosity. So this is the problem, blowhole. Now the next one, this is hot tear. Now this is one crack available on the surface of the product. This is called the hot tear. Now why this kind of problem happen? Generally different reasons it has. Like this is the outer surface here, this is greater compared to the inner surface. So the exposure area of the outer surface, this is higher compared to the inner surface. So here the solidification rate is higher compared to the inner one. So when there is deviation of the solidification rate, so obviously their thermal stress will develop. Okay, their thermal stress will develop. So at the time of solidification, due to this thermal stress, there is possibility of, that means develop that kind of crack. Okay, so this is one reason. Another way you can say that when the product will solidify, then it will shrink. Obviously for most of the materials at the time of solidification, it shrink. Okay, so here also it will shrink. So when it will shrink, at the mid portion, which one is available? At the center, there the core is available. Okay, so at the time of shrinkage, it that means apply huge amount of pressure on the core. Now if the core has collapse, that means collapsibility, then it will collapse and there is no resultant stress develop on the product. But if the core is very hard, what happened? So again there uneven stress will develop. The product tend to shrink, but at the same time the core resist it. So there is stress develop, and due to that there is possibility of development of crack. So this is the hot tear. Now the next one, this is misrun, incomplete pouring of the liquid material. So why this happen? Now the product thickness, suppose the product thickness is very less, so solidification rate will be higher. So if solidification rate is higher, then there is possibility of partial solidification before complete filling of the liquid material in between the cavity. So if that kind of phenomena happen, there this problem occur. This is called the misrun. There are higher solidification rate, very thin surface, that means very thin thickness. Okay, so due to that, before complete filling, their solidification happen. So that's why this portion cannot fill. Okay, and also you can say that if the pouring volume of the liquid material is less compared to the requirement, then also there that kind of problem happen. Now the next one, this is inclusions. Here you can see on the surface of the product there are some foreign particles like sand or dross. Okay, these are the foreign particles whose melting point temperature is above the melting point temperature of the liquid material. Okay, so you can see it on the surface. This problem is called the inclusions. Okay, and the last one, this is metallic projections. Metallic projection, this is the real cast. Okay, you can see this fin on the parting line on that zone. Okay, so this is called the metallic projection, and you can say that this is also one kind of defect. Okay, so these are some important defects developed on the cast product. Okay, sir, for better understanding, I think it will, that means please run the first video related to sand mold casting process.
Yes, I will do that. So I have already clicked on the video. It will take a little bit of time to come up. So it will just start in any moment. I request all to have your patience.
Sand casting. Sand casting is the most widely used casting process in manufacturing. The advantage of using sand to manufacture products of metal is that sand is very resistant to elevated temperatures. Almost all metal casting materials can be sand cast. Sand castings can range in size from very small to extremely large. Some examples of items manufactured in modern industry by sand casting process are engine blocks, machine tool bases, cylinder heads, pump housings, and valves. Now we will understand the process of sand casting in detail. First of all, on a clean floor, we will set the inverted drag box. Then we will place the pattern inside the box and pour the sand into the box. After that, sand is rammed and leveled off. The packed drag box is then turned over and cope box is placed over it. After that, second half of the pattern is placed exactly over the first half of pattern. Then the sand is filled and rammed tightly. Now two boxes are opened and pattern is removed with the help of screws. Boxes are again put back into position and clamped with rivets to prevent upper box floating. Gates and spruces are formed to pour the metal. Now the molten metal is poured into the mold. Then it is allowed to cool down for some time. After cooling, the final cast is taken out.
Okay, so I believe was the video. So Professor Sasthi, you can
Yes,
share
sir.
your screen again.
Yes, sir. Is it okay, sir?
Full screen.
Okay, sir. Okay, so the next one, this is classification of casting processes. So there are lots of demerits we already studied. Due to that, further improvement happened. So these are the classification. There are mainly four types: conventional molding process, then chemical sand molding processes, permanent mold processes, and next one, this is special casting processes. So under conventional molding processes, this is green sand molding, dry sand molding, flaskless molding. In case of the green sand molding, they are the moisture content, moisture percentage is available in the molding sand, and here that's why the name, this is green sand. And the next one, this is dry sand, there no moisture is available. Okay, under chemical sand molding process, this is cell molding, sodium silicate molding, no bake molding. Next, permanent molding process, this is gravity die casting and pressure die casting. And here for special casting processes, the types are investment casting, continuous casting, vacuum sealed molding, centrifugal casting, stir casting, plaster molding, evaporative pattern casting, ceramic cell molding, and slash casting. So there are lots of processes are available, but it's not possible to discuss about all. Here my topic for that means for the presentation, this is blowhole on the cast product, and this the product for the analysis I use here, this is prepared by the permanent molding process. So that's why here I again want to briefly discuss about the permanent mold processes. Now here I that means discussed about the sand mold casting process. There the main problem is for making each and every product, it's required to prepare the mold. and after solidification of the liquid material, there it's required to break the mold for getting the product. That means for each and every product there some separate mold is required, and after solidification it's required to break the mold. So the mold is no more permanent. Okay, it's required huge time, huge investment. Okay, so that problem we can solve by using the permanent molding process. Here the mold we use, this is metallic. Okay, so for repetitively for number of products we can use the same mold, and this mold we call it the die. Okay, so again here the die casting process. So the main drawback of sand mold process, mold need to be prepared for each of the casting produced. Okay, for each and every product separate mold is required to prepare. Now in case of the die casting process, the specialty is a metallic mold is used in the place of sand mold with which large number of castings are made. The metallic mold is known as die. Okay, here we use the metallic mold and we can use the same mold for number of products. Okay, repetitively we can use it. Okay, so obviously the die, that means the mold, here we use the material for that mold, this is metal or alloy, and the product material is also maybe metal or non-metal, but the melting point temperature of the die material, this will be obviously greater than the melting point temperature of the product. Okay, so the mold material, this is metal or alloys. Now here the types of die casting processes. Again there are two types mainly, gravity die casting and the next one is pressure die casting. Under pressure die casting there are two types, this is cold chamber pressure die casting and another one, this is hot chamber pressure die casting. So one by one I'll discuss all about that. Now the first one, this is gravity die casting process. So how we prepare the product by using this process? So there are two dies, that means two metallic mold. Okay, when you close these two dies, so here one die, this is stationary, this is fixed in its position, and another one, this is movable. Okay, so if you close these two dies, ultimately the cavity here developed, this is the negative shape of the product. Okay, this is the negative shape of the product. So before, that means filling the liquid material, what we do, at first we preheat the die. Okay, at first we preheat the die to, that means avoid the thermal shock, because the high temperature liquid material, when it will in contact with the die, there is possibility, that means there is huge difference between the temperature between die and the liquid material. So to avoid the thermal shock, at first we preheat the die material, the dies, then we spray some coating for easy removal and also for cooling purpose. We coat some material, okay, spray it on inner surface of the die, on the cavity. Okay, so after doing that we close these two dies, and there, if it's required to prepare the product with hollow cavity, then here again it's required to place the core. Okay, so this is the complete process. Before pouring, after that we pour the liquid molten material, okay, in between this cavity, and here the pouring happen by means of the gravity, no external force is here we use. So that's why this is called the gravity die casting process. Okay, this is very simple one. Now here are some examples of the products which we can prepare by using this process. This is aluminum piston. Okay, then the automotive engine block. Okay, so and also there are lots of products we can prepare. Okay, these two are the examples with, that means with respect to this process. Now the next one, this is cold chamber die casting process. There are two types under pressure die casting process. One, this is cold chamber, and another one, this is hot chamber. So by the name you can, that means you can identify. In case of the cold chamber, what is the, that means this that means the speciality here. In case of the cold chamber, the melting of the material happen in the furnace, which is not a part of the machine. That means we melt the material some another place. Okay, and then we carry the liquid material with this ladle for making the product in the machine. Okay, so that's why the name, this is cold chamber. So what are the parts are available in the machine? So here this one, this is called the short chamber. This cylindrical hollow portion, this is called the short chamber. And here on the short chamber you can find some hole. Okay, this is called the pouring hole. So we carry the liquid material with the ladle and we pour it through this pouring hole in between this short chamber. Okay, here there are two dies available, one stationary and another one movable. Also we use the ejector pin for after solidification for removal of the product from the die. Okay, so the simple process is we pour the liquid material in between the short chamber. Then here this is the plunger rod is available. Okay, after pouring we apply the movement of the plunger rod. So when plunger rod moves towards the die, so the liquid material compress and it will go towards the die cavity. Okay, so we that means we pour this liquid material through this plunger rod with pressure, and also we maintain this pressure throughout the solidification. Okay, throughout the solidification. So this is the process under cold chamber die casting. This is the first one. Then the next one. So these are the products which generally prepared by the cold chamber die casting process, pressure die casting process. This is pump housing, electrical motor frame. Okay, there are lots of others also prepared by using this process. And the next one, this is hot chamber pressure die casting. Here the specialty is the furnace. This is the part of the machine. Okay, here you can find the refractory lining for withstanding higher amount of temperature. Okay, so this is the furnace. In between the machine, melting happen. Okay, so the important parts here, this is again, this portion is called short chamber. Okay, again you can find some pore in this short chamber. There the melting happen in the furnace, so the molten material can flow through this pore in between the short chamber. Okay, so this is called the gooseneck. Here these two dies, one stationary, another one movable. The ejector pin is also available, and also there we use cooling system for increase the die life, and also for increase the die life and for better quality product. Okay, so first through this pore the liquid material fill in between the short chamber, then we apply the plunger. Okay, that means we apply the force or pressure on the liquid material. So when we apply the plunger, first it closes the pore, this hole, that means for the flow of liquid material in between short chamber. Okay, then it will apply pressure on the liquid material and it will go towards the cavity in between the die. And also here we maintain the pressure throughout the solidification, and after solidification we get the product. Okay, so this is the process of hot chamber pressure die casting. So the main difference between hot chamber and cold chamber, in case of the cold chamber, the melting happen in the furnace, which is not part of the machine, and in case of the hot chamber, the melting, that means the furnace, this is the inbuilt part of the machine. Okay, here some example. One example, this is carburetor body. This can make by using this process, hot chamber pressure die casting process. Okay, now before going to the detailed discussion on the specific topic, this is blowhole case study. Here it is required to discuss something about some important topics, some important terms. Okay, so the first one, this is biscuit. These are the terms used in die casting. First one, this is biscuit. Excess of ladle metal remaining in the short sleeve of the cold chamber process. It is the part of the cast short and is ejected from the die with the runner and casting. Okay, so what biscuit means here, look on this diagram, in this diagram. So the material available in the short chamber, there when we apply the plunger force, then the material flow towards the cavity. Okay, but some material is also available in the short chamber. That means calculate the volume like that way. Okay, so this material is called the biscuit. Okay, and on this material, that means on the dimension of this material, the quality of the product depend. Okay, now the next one, this is blowhole. I already talked about this many times. Like the blowhole, this is voids or pores occur due to entrapped gas or volumetric shrinkage during solidification. This shrinkage during solidification, this is condition is usually evident in heavy section, okay, where the section thickness is very high. That means thickness is very high. That means huge amount of material available. So huge amount of material means there the temperature capacity is higher. Their temperature capacity higher, and it's take time, larger time for the solidification. Okay, so there that kind of problem can occur, can happen. Okay, so this is called the blowhole. Due to the entrapment of the gas, okay, it cannot escape, and ultimately it makes some impression on the product surface. This is the this impression like voids or pores. Okay, so this is called the blowhole. Now the filling ratio, volume or weight of usable casting product divided by the total volume or weight of metal injected into the die, that is expressed as a percentage. That means the total volume required for making the product, only the product, and total volume required, volume of the material, molten material required for the total process. The ratio between these two, this is called the filling ratio, and it is good practice to, that means to use lower filling ratio. Okay, lower filling ratio, this is the good practice. Now the next one, this is cavity fill time, the critical time that takes to fill the die cavity. This time has a profound effect upon the amount of premature solidification that occurs before the cavity is completely filled with metal. So the process is first liquid material fill in the short chamber, then we apply the plunger, then it will travel through the that means short chamber towards through this that means gating system, then ultimately to the cavity. Okay, so that total travel needs some time, but what will be the time? What is the best practice to, that means for calculation of the time? Is it very high or less? Now if we use very high time, that means very slow travel of the plunger, what happens? There possibility of that means solidification of the material before complete filling. Okay, now if we that means use very less time, that means very high plunger speed, so what happened? The turbulence occur on the liquid material, ultimately affect on the quality of the product. Okay, so we cannot choose the very fast time or slow time. So here it's required to choose the optimum time, which is called the critical time. Okay, this is a very important one for with respect to the quality of product. Now the next one, this is gate, the orifice through which the casting alloy exits the runner and enters the die cavity. The orifice through which the casting alloy exits the runner and enters the die cavity, this is called the gate. Okay, so if you remember the total flow channel in case of the sand mold casting, the elements are, first one, this is pouring basin, then sprue, then runner, then gate, and then the cavity, and after that the riser. Okay, here same, this is the orifice through which casting alloy exit the runner and enters the die cavity. That means just before the die cavity, the portion we call it gate. Also the entire ejected content of the die, including casting, gate, runner, biscuit, sprue, overflows, vent, and flask. So these, all these elements we consider it as gating system. Okay, now the next one, this is ingot. This is casting alloy formed in a convenient shape for storage, shipping, and remelting. So this is the stock, raw material with definite that means shape. This is called the ingot. Next one, this is overflow. Overflows are cavities and passages in the die which act as vents for air to escape and traps for excess metal flow. So there intentionally we use, that means we design the die like that way. There some excess amount, excess volume of liquid material, that means with some particular zone of the product. Okay, so this is not required, but this is not required for the product, but required for the quality product. Okay, So overflow, this is excess volume of the liquid material, which is not related to the product dimension. Okay, so overflows are cavities and passages in the die which act as vents for air to escape and traps for excess metal flow. Now the preheat, the practice of heating a die casting die to at least 200 Fahrenheit above ambient temperature to minimize the thermal shock from the first few shots in a production run. I already told related to this. Okay, so the die temperature, this is initially at room temperature, and that means the material we use for making the product, this is above melting point temperature. Maybe it's 700 degrees centigrade or 1000 degrees centigrade. Okay, so there is huge difference between these two, die temperature and the material product, that means molten metal temperature. So to avoid the thermal shock, there we preheat the die material. Next one, runner. This conduit is the main part of the metal feed system that transfers the casting alloy from the biscuit or the sprue to the gate. Okay, so this is the runner. So from this biscuit to the gate, this channel from biscuit to the gate, okay, this conduit, this is called the runner. Now the next one, this is short sleeve, the steel tube in the cold chamber process that holds the casting alloy and through which the plunger tip moves the metal into the metal feed system and the cavity. Okay, so this hollow cylinder where initially the molten metal fill, okay, this is called the short sleeve. Okay, and there after filling of the liquid material through this short sleeve we apply the plunger. Okay, we move the plunger. Now next one, this is sort of the space of the parting plane of the die that provides an unrestricted area to apply the clamping force of the machine to seal off flash generation. Okay, there the possibility of development of the flash. Okay, so we can avoid this by using the sort of. Next, undercut, recess or cord hole position perpendicular to the die parting that prevents ejection. Okay, so recess or cord hole position perpendicular to the die. Okay, this is called the hole position perpendicular to the die, this is called the undercut. Now the vent, a shallow passage of the die cavity at the last place to receive liquid metal that allows air from the metal feed system to escape as the cavity is filled. So this is very much important, vent, because the burned gases can escape from this space. Okay, so that's why it's required, the shallow passage. Okay, air, that means allow air from the metal feed system to escape as the cavity is filled. Okay, this is called the vent. Now these are the important terms related to pressure die casting process. So next I'll that means discuss about the particular topic. This is the case study on blowholes. But before going to the next slide, I want to play the next video. So kindly run it.
Me to run the video now? Hello, you want me to run the video now? Okay.
Yes, sir. Yes.
I will do that. So video will come up anytime now again.
Hot chamber die casting. Let us see a 3D model of a hot chamber die casting machine. The hot chamber die casting machine has moving die, fixed die, ejector plate assembly, furnace, closing die, cavity, ramp, inlet port, molten metal, and inlet nozzle. When the ram is raised, it opens the inlet port in the chamber and allows the molten metal to fill the chamber. In operation, plunger is forced downward for closing the port and then forces the molten metal into the cavity. After solidification, the die will open and eject the parts. Cold chamber die casting. Let us see a 3D model of a cold chamber die casting machine. A simple cold chamber die casting machine has injection unit, funnel, fixed die, moving die, platen, tie bar, plunger, short sleeve, spur, cavity, gate, and molten metal. Molten metal is transferred from heating furnace using transfer ladle and poured into the sleeve. Plunger pushes the molten metal through the spur to fill the cavity in die. The moving die moved back and casting is ejected using ejector pins. Thus, casting is produced using a cold chamber die casting machine.
Okay, so that was the video. I will just very quickly shift back. Professor Sasthi, you may again present. You may again present.
Okay, sir. Okay. Okay, now comes to the next topic. Here I want to discuss about one project where one product was prepared by the cold chamber pressure die casting method with design data and process. But the problem happened there was in the product, one severe defect occurred on the surface, which was blowhole. So the target of the project was identify the problems, analysis on the problems, and also sort out of them. So here, this is the component. Now look on the surface of the product. Here you can find in this area in on the surface of this product, blowhole problems occurred. Now, if you generally want to define the blowhole from the metallurgical point of view, you can say that a defect in a casting or ingot caused by the escape of gas. Okay, so on the product surface there are some holes are available, so this is the kind of blowhole. Okay, now reason for blowhole. So we categorize the blowhole into two forms. The first one, this is shrinkage porosity, and the next one, this is gas porosity. Okay, now one by one we can talk on these two. When it was analyzed to find the reasons for shrinkage porosity, and also what are the countermeasures to solve this problem, then it was found that we can measure or we can identify the shrinkage porosity only by seeing the surface by naked eye. Visually you can see this, it is a very uneven shape, and reasons for that may be wall thickness variation. Okay, the first one, this is wall thickness variation. So due to the wall thickness variation, there is possibility to occur shrinkage porosity. I can say you where the wall thickness is very high, there are heat concentration also high. So if their wall thickness variation is available, then there is imbalance of heat concentration, so there is possibility of shrinkage porosity. Okay, so the first reason here, this is wall thickness variation. The second one here, this is thermal balancing due balancing die unbalanced. So what is thermal balancing? The heat we added to the die through melted metal in each production cycle, okay, that we have to remove through die spray, die cooling. Okay, so heat we apply in the process, it's required to remove it by that means heat addition happen with some process, and also heat rejection happen with some another processes. The main thing is first there are that means it's required to release this heat, and for balancing of this heat, this phenomena, this is called the thermal balancing. So there are mainly 4 phases through which thermal balancing happen. So the first one, this is melt contact with the dyes. When liquid material within contact with the dyes, then that means heat addition take place on the dyes. Okay. In the second phase, dye exposure to the ambient environment after the casting ejected here. That means after rejection, that means ejection of the product. Okay, the dye, this will in contact with the surrounding atmosphere. Okay, so then heat, that means heat transfer happen. The third one, duration of cooling and lubrication spray on the dye, and the fourth one, this is dye exposure again to the ambient environment before the next cycle begin. Okay, so this process of heat addition and removal keep continue in a equilibrium for the sake of good quality of casting, to increase dye life and to increase casting strength. Okay, so if we not properly maintain thermal balancing, what happened? It either overheated or overcooled, and various problems happened in machine, system, or product. Like for fast heat releasing, there may be cold shut, chill marks, or shrinkage porosity developed on product surface. Like that, for slow heat releasing, there are higher solidification time and lesser productivity. Okay, so here thermal balancing required to overcome shrinkage porosity. We can do it either by adding or removing the cooling line. Okay, so this is the next one. Now the next one, this is a less metal pressure. So when molten metal is still held in the die, extremely high pressure is applied. Okay, we apply this pressure by means of the plunger. So this is called the intensification pressure. Okay, so this high pressure compresses any gas entrapped into the metal and feeds additional metal into the cavity to compensate for the shrinkage of the metal as it solidifies. Okay, first it compresses the liquid material. Okay, and also that means if there are some cavities available, so it due to this compression, this can remove. Okay, so that's why this thing is very much important. This intensification is you can say that is only effective on shrinkage porosity. Okay, this is one important thing. This is effective on the shrinkage porosity, and it is not, that means cannot eliminate the, that means the porosity defect related to gas. Okay, this is only effective on the, that means the shrinkage porosity. Now the next one, this is silicon percentage. Now with different studies, it's found that with silicon percentage, that means when we use the product material with higher silicon percentage, there the shrinkage porosity defect happen, this is less. Okay, so with higher shrinkage porosity, that means higher silicon percentage, we can avoid this problem. Okay, higher silicon percentage and higher melting point temperature. Okay, now the next one, this is less biscuit thickness. Here this is very much important. This is biscuit thickness. Biscuit, this means I already told that excess of ladle metal remaining in the short sleeve of the cold chamber process. So this is the part of cast output. And now the thing is, if biscuit thickness is less, then what happened? Biscuit thickness is less, then what happened? That means initially the solidification take place from the biscuit, because their thickness is less compared to the product thickness. So where thickness is less, that means their solidification rate is higher. So the direction of the that means the direction of solidification take place from the biscuit towards the product. Okay, initially that means at first the biscuit solidify, then getting system, then finally the product. Okay, now if the biscuit thickness is higher compared to the product thickness, what happened? Initially the solidification take place first on the product, then it go towards the biscuit. So which one is best? If biscuit solidify first, then porosity take place on the product, and if product solidify first, then porosity happen on the biscuit. Okay, we are interested with the product, so that's why it's best practice to choose higher biscuit thickness. Generally we choose it 10 to 15 millimeter greater compared to the higher that means thickness of the product. Okay, so these are the important reasons for shrinkage porosity, and all these are the countermeasures. Now the next one, this is gas porosity. This is also another category. The first one here, you can identify it by simply looking the surface of the product. It is spherically safe. It is spherical safe when the entrapped volume of gas is higher compared to the gas solubility. Okay, the metal then the air dispersed as small sphere on the high pressure air. Okay, when the metal fills the cavity. Okay, that means there the air is available with high pressure, it cannot escape. Okay, so then it make this kind of problem, and this is look blackish, and the inner surface is very smooth. Okay, this is that means you can say that the difference with the gas porosity and the shrinkage porosity. This is blackish and very smooth inner surface. Okay, so what are the reasons and what are the countermeasures? So first one, this is excess plunger lubrication. So if the lubrication we use, the amount of lubrication is very high, it is not good. It is best practice to avoid the lubrication or use the less amount of lubrication. Okay, if there is lubrication on the that means front of the plunger, then it will mix with the that means molten material. So it's due to that it's developed the gas. Okay, so here the countermeasure is check and avoid putting lubricants in front of the tip. Okay, now the next one, this is weight die insert. So check die insert before closing. So if obviously that means weight, that means their moisture is available, it's not good. So check die insert before closing. Now undesired slow short velocity, the plunger movement. Okay, the plunger movement, if it is very slow, not good. Slow means that means opposite wave can develop on the liquid material. Very high speed, that means turbulence. Okay, so it's required to optimum speed. So undesired slow short velocity, calculate desired slow short velocity. Now the next one, this is metal treatment, degassing, cleaning. Okay, so obviously it is before preparation of the metal, that means filling in the cavity, it's required to treat it by like degassing or cleaning. Okay, if gas or the inclusions are available, it's may that means due to that their gas porosity can develop. Sharp metal entry through runner. Okay, so sometimes you can find the runner shape. This is like there are some blind edge or sharp corners are available. So where there is sharp corner or blind point, so there at the time of flowing of the liquid material, there is possibility of development of turbulence. It's not acceptable. Okay, so that's why generally we that means all times avoid the sharp corners or blind edges. So check there any sharp edge and blind ends. The next one, this is small size vent or jam. So vent, this is very important. All the gases can escape through this. If gas is available, then it can that means produce the blowhole. So if the vent size is less or they are jam, that means it's not clear. Okay, so then the gas porosity happens. So check the correct size. So these are the main reasons under two different category, shrinkage porosity and gas porosity. Okay, now for the analysis here, the process parameters, there are three different dyes used like D1, D2 and D3, and different process parameters choose. Okay, different process parameters with respect to three dyes. Okay, like the number of cavity, overflow weight, production weight, runner weight, casting weight, gate passing, like sleeve fill up ratio, production weight, gate area, gate ratio, etc. Okay, so these are the process parameters with respect to three different dyes for the analysis of the product to eliminate the blowhole. Okay, there are three different dyes with different variables with respect to different process parameters. Okay, their analysis happened with respect to these process parameters. Now the next one, this is sludge factor. Sludge, that means the impurity. Okay, and always it's best practice to use that means to take material with less sludge factor. The impurities generate at the time of melting, so we generally choose that kind of alloy or material where the sludge factor is less. There are some standard calculation is available. Okay, sludge factor is equals to 1 multiplied by 1 weight percentage of iron plus 2 multiplied by weight percentage of manganese and 3 into weight percentage of chromium. So this is that means the material used for this analysis. They are the sludge factor. This is 1.32 and it should be less than 1.85. Okay, always it should be less than 1.85. Now here these runners, when it's found that their blowholes develop on the product, then the modification, that means after identification of the problem, there modification done on the process. Here this is the runner. Okay, there are two leg. This is the runner. Okay, what's the problem here? In the first one on the die, you can find that the sharp edges. Okay, they are the sharp edge, here the sharp edge. Okay, so you know that sharp edge, this is not suitable one because turbulence happen. Okay, so to eliminate this problem, this is the modified diagram. This is the modified, that means design. Here the edges is not sharp, this is even. Okay, it's continuous. This is the first modification, runner sharp edge. Here this is the opposite side of the runner. Here you can find that this is there the sharp edges are available. So this is the modified diagram, the design there. It's eliminate the sharp edge by provide the radius. Okay, this is the next one. Now this is the bend status. This is the rapid observed on the product. There are 3 dies, D1, D2 and D3. So total bend, this is 1.21 for D3. For D2 this is 1.71 and for D1 this is 1.52. These are the total bend. Check for excess machining margin. So cast dimension, this is 23.2 millimeter, and there after that means casting, their machining is required with respect to the product prepared by 3 dies. The machining required, this is 0.86 millimeter for D1. For D2 this is 1.06. For D3 this is 0.94 millimeter. So the final dimension, this is 22.34, 22.14 and 22.26 millimeter. So blowhole status after machining. So after machining, when it that means analyzed for finding the blowholes, so it's found that for dies D3 and D2 there are no problem. That means with bend 0.8, 0.9, 0.8, 0.8, 0.7, all the, that means there are no, that means all the products, this is acceptable, this is okay. Okay, only here you can find with bend 0.3, that means which is less than 0.5, there that means there is possibility of development of blowhole. So there one myth is available where there is higher bend on the product or the getting system, there are possibility of that means development of blowholes, but it is not true. Okay, blowhole, this is not so much related with the bend. Now here that means here some important problems we that means you can identify. There this is the runner, okay, with 2 leg. This is the biscuit runner, and you can say that in this side this is gate. So metal can flow from this side to that side. Okay, here you can find that the dimensions are available. This total length is divided in different zones like A, B1, B2, sorry, B1, C1, D1 and B2, C2, D2. So A, this is 7.35 centimeter square, B1 this is 3.6 centimeter square, C1 2.4 and D1 4.2. That means from biscuit to the gate, okay, the cross section of the runner, this is gradually increasing. Okay, so area is suddenly increasing, dropping the gate velocity and casting pressure. So these problems happen if the gate area gradually increase towards the, sorry, the runner area increase towards the getting that means gate or the mold. What happened? Actually its velocity this will reduce, and it is not good Okay, velocity, when velocity reduced, that means it takes higher time, it carry the gases. Okay, so this is not good. So in the next slide, this is the modified, that means data runner design analysis for D1 and D2. Here the dimensions are A, this is 10.21, C1 4.38, and D1 4.28. That means the area of different zones towards the getting system, this is gradually decreasing. So you can get the higher velocity and also optimum pressure. Okay, so this is the modification. So here are some guidelines for proper design of the runners. Runner area must be ever decreasing from sleeve or screw to gate for maintaining the proper velocity and pressure. Next one, runner design must be smooth and rounded. There are no sharp corners or blind edges, that means permitted. Then smooth and ever decreasing can be made much smaller and more efficient, saving money and energy. Okay, start at the casting, increase area 3% to 5% at every bend and 3% to 10% at Y junction. So these are the guidelines for proper design of the runner. Now the next one, slow short speed validation. So here 4 different sample, okay, with respect to different slow short speed, okay, and also the distance traveled by the plunger, speed and the short distance. Okay, so there are 3 samples, 1 2 3 4, with respect to the distance traveled by the plunger with different distance and slow short velocity. Okay, so you can see that there for most of the products, they are the blowhole developed. This is not that much. Okay, so that you can reject this product. So that means I can say that 2 3 and 4, all these are very good product with minimum amount of blowhole. But the best one here, this is slow short velocity. This is 0.2. The third one, this is 0.2 meter per second with distance traveled by the plunger. This is 300. This is not 360. This is wrong. This is 300. Okay, so this is the third one, third trial. This is the best one, where the blowhole problem is minimum. And this is the final result. Okay, so after all these modifications, it was found that that means the product with lot size, the row third and fourth, they are all the products acceptable. Okay, there are no rejection happen. Okay, so if you do all these modifications, okay, if you, that means modify the process, modify the design, then you can eliminate the blowhole problem. So that's all. Okay, sir, thank you.
You, Professor Sasthi. So would you like the poll to be shooted now, or what order
Yes,
would
sir,
you prefer? Okay.
Yes, sir, poll.
So I have shooted the poll and requesting all members to vote at your earliest. We will wait for 1 minute as always. Which defect is caused due to the conversion of moisture of steam because of the heat of molten metal? Okay. So we have already reached 40% votes. I request all members to vote at your earliest. We have reached 52 seconds. We will be waiting for 8 more seconds. So it's already 56 seconds, and we have reached 55% votes today, which is again comparatively better. I close it and I share the results. So kindly check the results. 61% people says blowholes, that is which defect is caused due to conversion of moisture of steam because of the heat of molten metal. Is 61% have gone for blowholes. Open holes 18%, 17% says air inclusion, and 4% says cold shut. Professor Sasthi.
Okay, sir, the answer is blowhole. So when they are that means defect happen due to the entrapment of gas or vapor, it actually gives some impression on the product surface, like the hole, the pores. Okay, so the problem here, this is the blowhole, sir. This is the right answer.
Okay, so 61% have gone with your right answer. So I hide it, and now I will check whether there are any questions. There were one or two I saw. Yes, so let me try to reach the first question first. How is the blast furnace different from an arc furnace? Asks Srimanandi madam. How is the blast furnace different from an arc furnace?
Sir, that means the total technology is completely different. Okay, in case of the blast furnace, there we use that means the fuel. This is coal. Okay, this is coal. We use the fuel, and it's run for long time. But in case of the arc furnace, they are the that means due to the temperature developed due to the electrical arc. Okay, so this is the difference.
Okay. Okay, fine. Professor Sandeep Kumar Chaudhary asks, how much is the filling ratio for cold chamber die casting and hot chamber die casting? Are they same? The filling ratio.
So actually, sir, a particular that means number I cannot that means say, but I think that means the ratio for these two processes will be different. It depends on the product, sir. It depends on the product, which material we choose, what's the product dimension, what's the machine that means machine dimensions, machine capacity. Okay, it depends on all these things, and it's required to calculate the filling ratio with respect to that. So there is no particular number for all the products. Okay, but that means that the values will be different.
Okay. Professor Sandeep Kumar Chaudhary has got a comment also. He says die cooling is done with pressurized cold water flow through pipelines placed inside the die plates.
Yes.
Okay. Okay. How pinhole defect can be overcome? Asks Professor Rahul Malik.
So pinhole different actually happened due to the that means due to hydrogen gas. Okay, sir. So at the time of melting in the furnace, there the hydrogen gas can entrap into the molten metal. So when we fill it into the cavity at the time of solidification, these hydrogen gas escape from the metal, and due to that, this pinhole problem there happen. So we can eliminate this problem by melting the liquid material in vacuum chamber by the degassing. Okay, that means our intention is to that means separate the hydrogen gas from the molten material.
Okay, thank you, Professor Sasthi. Professor Sandeep Kumar Chaudhary also seems very pleased with your answer. He said, well said, thank you. Okay, thank you. Thanks to all IEM and UEM family members. Thanks, Professor Sasthi. It was a nice presentation. Thank you.
Okay, sir.
Thanks
Thank you,
to
sir.
all of you.